Hello and welcome to my next presentation on thermal physics, which covers specific heat capacity, latent heat of fusion and the latent heat of vaporization. I'm Bernard Taylor and we're dealing with heat. So what about this part of a poem from Robert Frost? How often already you've had to be told, keep cold, young orchard, goodbye and keep cold. Dread 50 above more than 50 below. There I am, Fez Physics, and if you're interested in tuition, please do contact me. Now, if we have a beaker with water in it, and we have a thermometer there, the thermometer reads the temperature theta. If we increase the amount of energy we provide, then the temperature theta will increase. So delta theta, the change in temperature, is directly proportional to E, the amount of energy we provide, whether it's from a Bunsen burner or an electrical heater. Let's go further. If we have the same amount of heat energy supplied each time, but to different masses of water, then with less water, we have a bigger temperature increase. So delta theta is proportional to 1 over m. Now, different liquids, indeed different solids, different gases, will give us a different temperature rise when we provide the same amount of energy. And I'm saying delta theta is proportional to 1 over c. And what is this to do with? Well, it's to do with the number and the mass of atoms, the nature of the bonding between the atoms in that material, but I'm going to gloss over that for the moment for the purposes of A-level physics and IB physics. So what have we established? We've established 3 relationships and we can put them together so that delta theta is proportional to E over mc. Yes, I know we haven't defined what C is. We'll come on to that in a moment. If we're using SI units for energy, joules, kilograms, degrees centigrade or Kelvin, then we can move straight from this proportionality to an equation. So delta theta equals E over m times C. That leads us to E equals m times C times delta theta. Okay, I've made it clear what the units are there, but what about C? Well, I'm repeating myself and I'm saying that C is something that we're going to call the specific heat capacity. So C equals E over m times delta theta. Its units would be joules, kilograms to the -1, degrees C to the -1, or if we're using Kelvin, joules, kilograms to the -1, Kelvin to the -1. And this is something we really need to know. The specific heat capacity is the amount of heat energy needed to change the temperature of 1 kilogram of a substance by 1 degree centigrade or 1 Kelvin. Different substances have different specific heat capacities. Now, look at this here. Water, 4,200. Aluminium, 8,800. Sand, 800. In all cases, joules, kilograms to the -1, degrees C to the -1. The specific heat capacity is the amount of heat energy needed to change the temperature of 1 kilogram of a substance by 1 degree centigrade or 1 Kelvin. Yes, I'm repeating myself. I'm allowed to. I'm a teacher. Don't teachers do this all the time? It is a measure of the thirst of a substance for heat energy. Some substances have a greater thirst than others for heat energy. Some substances require more heat energy than others to produce a certain temperature rise in a particular mass. Specific means it's specific to 1 kilogram. We've got a unit mass of 1 kilogram. And let's remember that equation. E equals mc delta theta. Now, the specific heat capacity of water is a massive 4,200 joules, kilograms to the -1, degrees C to the -1. And for sand or earth, it's about 800. In summer, the sea around the UK warms up more slowly than the land. In winter, the land will lose heat energy relatively quickly. After all, the land, the sand, the dirt, the soil, hasn't stored much heat energy compared with the sea. In winter, the sea will cool more slowly since it stores a lot of heat energy, and this will moderate the climate of the UK, being close to the sea. So in the UK, we generally have warmer winters than deep in the heart of Europe and Holy Mother Russia. But it's not as simple as that, because of course, if you're a geography student, you'll be aware that what used to be called, when I was at school, the Gulf Stream, but now we refer to the North Atlantic Conveyor, which carries warmer waters from the tropics up towards the British Isles, and that again, in carrying that warmer water, that moderates the climate. It'd be interesting, or perhaps not so interesting, to see what the effects of recent research would be of the melting of the Greenland ice caps on the North Atlantic Conveyor. It could have an absolutely disastrous effect on our climate. Here's another experiment, a classic experiment. And we've got an electrical immersion heater in some water, in a beaker. We've got a thermometer, we've got a DC power supply, 12 volts, we've got an ammeter and a voltmeter. And with 0.4 kilograms of water in my example, the temperature rise is 4 degrees centigrade. We're heating this water for 5 minutes, and we might say that the electrical energy supplied to the heater equals the heat energy absorbed by the water, simplistically. So V times I times T equals m times c times delta theta. And we put the numbers in, both sides of the equation, and what we're trying to do is find a value for C, the specific heat capacity. And when we do the maths, we find that we get 4,000 joules per kilogram degree C to the -1. Okay, but isn't this a little bit lower than the book value? What assumptions have we made? Well, first of all, we've got to be careful in experiments like this that we stir the water. Why? Well, convection currents may mean that the water in the top of the beaker is warmer than the water at the bottom of the beaker. So we need to have an even temperature and to record that accurately with the thermometer. But there's also other points. What about heat losses to the surroundings? Yeah, we need to perhaps take that into account. But there's also a few other points we can make. Actually, the electrical energy supplied to the heater goes to heating the water. It also goes to heating the glass beaker. It also goes to heating the metal of the heater itself and the thermometer, as well as heat losses to the surroundings. So we might have had an m.c.Δθ term for the glass, for the heater, and for the thermometer itself. We could also have put a lid on the beaker. We could have lagged or insulated the beaker to reduce heat losses to the surroundings. And we've got to be careful about these points in exam-style questions. Here, we've got an exam question, past exam question. The heating element of a hairdryer supplies 2.1 kilowatts to the air flowing over it. The hairdryer is plugged in to the 230 volt main supply. What is the minimum current flowing in the heating element? Well, we've got power, we've got voltage. Yeah, power equals V times I, so I equals power over the voltage, and we get about 9.1 amps. Right, fine. Let's go a bit further. The fan in the hairdryer blows air at 20 degrees centigrade across the heating element. which will essentially be just a filament, at a rate of 0.068 kilograms per second. Calculate the temperature of the air coming from the hairdryer, the output temperature of this air. Okay, we're given the specific heat capacity of the air. So what are we going to do here? Well, we're going to consider 1 second. And 2.1 kilowatts is 2.1 times 10 to the 3 joules per second. E equals mc delta theta. So delta theta equals 2.1 times 10 to the 3 over the mass delivered in 1 second, 0.068, times C, the specific heat capacity of the air. And we get delta theta is 30.6 degrees centigrade. But hold on, actually the temperature of the air coming out then, we need to add on the 20, so we get 50.6 degrees centigrade. Let's not have too many significant figures. Let's round that to 51 degrees centigrade. And let's move on. Describe the energy changes that happen as the air is blown over the heating element. Well, the hot filament has vibrating atoms. Heat is vibration. And as the air molecules come across the vibrating atoms of the hot filament and collide with those vibrating atoms, the air molecules will gain kinetic energy in bouncing off and some vibrational energy as well. So we could say the thermal energy goes to the kinetic energy of the air molecules plus the vibrational energy of the air molecules, which of course is a form of potential energy. Now, here's a challenge for you. Using an electric kettle from home, can you estimate a value for the specific heat capacity of water? Can you do the experiment? A few hints. Look at the bottom of the base plate of the kettle to find the power rating. Use a timing device. Oh yeah, we're going to heat some water for a certain number of seconds, perhaps a couple of minutes. And what else? Well, we want E equals mc delta theta. What about M? Well, my hint to you is pour some water into the kettle, into the empty kettle, using a measuring jug. And remember that 1 gram is 1 cubic centimeter, which equals 1 milliliter. Measuring jugs are often marked in milliliters. And yes, you're going to have to bring the water to the boil. Oh, make an estimate of room temperature. And let's assume that it's going to boil at 100 degrees centigrade. So that's a challenge for you. Now for something completely different, as they say in Monty Python, except that this is not quite so amusing. What have we got here? We've got an electrical immersion heater in some crushed ice, in place, in a measuring cylinder, in a filter funnel, and we've got a beaker to contain the melted water. And let's look at it. We've got the voltage, the current, the time, we've got the mass of the melted water, we know the electrical energy supplied, V times I times T, and that works out to be 2,160 joules in this example. So I'm saying that 8 times 10 to the minus 3 kilograms of ice is melted by 2,160 joules. So 1 kilogram of ice is melted by 2,160 over 8 times 10 to the minus 3, which is about 2.7 times 10 to the 5 joules to melt 1 kilogram of ice. Okay, so I've repeated myself here in the first line, and I've said that this was close to the expected value of 3.34 times 10 to the 5 joules per kilogram. And what is this? The specific latent heat of fusion of ice is the amount of heat energy needed to change 1 kilogram of ice at 0 degrees centigrade into water also at 0 degrees centigrade at the same temperature. No temperature change on melting. The specific latent heat of fusion of ice is 3.34 times 10 to the 5 joules per kilogram. And this value would be given to you in an exam. The symbol that's often used for that is L. L. So how much energy is needed to melt 250 grams of ice at 0 degrees centigrade into water at 0 degrees centigrade? How much energy? E equals M times L. 0.25 times the latent heat of fusion of ice, and we get 8.35 times 10 to the 4 joules. Okay, straightforward enough. Remember this relationship. E equals ml for changes of state, and melting is a change of state. Why latent? The word latent means hidden. It's heat which is gained or lost during a change from a solid to a liquid, or vice versa, without causing a temperature rise or fall, is called the latent heat of fusion. The latent heat produces a change of state and not an increase in temperature. In solid ice, we have a crystal lattice. The molecules vibrate to and fro about fixed positions in the lattice. And to melt that ice, energy is needed to overcome the attractive forces holding the molecules together. The latent heat provides this energy and allows the molecules to move into the liquid state at the same temperature. Incidentally, I'm not going to stress this point too much, but the latent heat increases the potential energy of the molecules rather than their kinetic energy. An analogy is with two objects joined by an elastic band. If we pull them apart against the attractive force provided by the elastic band, stretching the elastic band, moving them further apart, doesn't the system have more potential energy? Yes, it does. Now, on the left-hand side, that's me in the cap at Devil's Bridge in Wales, having a go at driving this mini locomotive, steam locomotive. Can we see steam? No. Steam is an invisible gas at 100 degrees centigrade. Steam is transparent. What we can see is water vapor, but what we refer to as water vapor, we sometimes use the term steam. But strictly speaking, that's not correct. If we look just above the spout of the kettle above, we see, well, what do we see? We don't see anything, because the steam is at 100 degrees centigrade and it's transparent. In coming out, it then cools and becomes water vapor. I left my 3 kilowatt electric kettle switched on for 2 minutes while the water boiled away. Right, it already reached 100 degrees centigrade. 160 grams of water was vaporized as steam, and then water vapor. 0.16 kilogram was vaporized by 3 times 10 to the 3 times 2 times 60 joules. We need to work in seconds, we need to work in watts. So 1 kilogram was vaporized by 2.3 times 10 to the 6 joules. So 2.3 times 10 to the 6 joules per kilogram. The specific latent heat of vaporization of water is the heat energy needed to change 1 kilogram of water into vapor without any rise in temperature. The boiling water was at 100 degrees centigrade and the steam was at 100 degrees centigrade. Okay. An electric kettle is marked 2.5 kilowatts. The kettle is brought to the boil, weighed and boiled for 10 minutes and weighed again. The specific latent heat of vaporization of water is given. Calculate the mass of water vaporized per minute. Well, let's calculate the mass of water vaporized in total and then work out the mass of water vaporized per minute. You might want to pause and try this calculation yourself. So the electrical energy supplied is power times time, 2.5 times 10 to the 3 times, well, 10 minutes, that's 10 times 60 seconds, and that's 1.5 times 10 to the 6 joules. M is, and we usually use the term small m, is the mass vaporized. E equals ml again, so M equals E over L. And a simple calculation gives us that mass vaporized is 0.664 kilograms in 10 minutes. So we work out the mass vaporized per minute as being 0.0664 kilograms per minute. Well, let's not have quite so many significant figures, 0.07 kilograms per minute. And this again is a past exam question. Now, let's look generally at this process. Starting at the bottom, in moving from a solid to a liquid, we've got a change of state, melting. In going in the reverse process, going from a liquid to a solid, we've got freezing. Okay, if we go from a liquid up to a gas or a vapor, there's a change of state. And we've got vaporization. And if we go in the reverse direction, we've got condensation. So looking at what I'm saying on the right-hand side, vaporization, the latent heat of vaporization given to a liquid will turn it into a gas or a vapor. Condensation, latent heat of vaporization is removed from a gas or vapor. The reverse process. Melting, latent heat of fusion is given to a solid to melt it. Freezing, latent heat of fusion is removed from a liquid. Now, we often get questions, past exam questions, which ask us to use or to be aware of changes of state and to use specific heat capacity. I'm not going to go through this full example, but schematically we can see what's happening if we go from left to right. 2 kilograms of ice at 0 degrees centigrade. First of all, it's melted. There's a change of state. So the amount of energy would be E equals M times L. If that water, that same mass of water, goes from 0 degrees centigrade to 100 degrees centigrade, then we'd use E equals m.c.Δθ. And then, if we've got that water which is boiling, turning into steam, into vapor, also at 100 degrees centigrade, then again we would use E equals ml. So be aware of these transitions. And thank you very much. That's Phys Physics, and stay tuned for my next Phys Physics video every Friday, 2 o'clock Greenwich Mean Time. And keep working.